Thank you, Mr. Chair. Good morning, everybody. I'm so happy to give you can come to my talk. Thanks so much. Yesterday, I talked about the classification of Blazars. Today, I'll focus on the beam effect. This is the outline of my talk. First, I say something about the beam effect in the baby Blazars, and then I talk about the Hubble diagram. Then I talk about how to determine the Doppler Factor, and also we use the two-component model to separate the emission in the X-ray band. And also, I'll talk about the relationship between BNI object and FSI Qs. Okay, now the beam effect, because of the extremely observational property of Blazars, people proposed a model. In this beam model, there is a massive black hole, and this is the jet. When the jet can point to us, there is a beam effect, just as Elena said that a few days ago. And this the delta is a very, very important factor. We call it depends on the bottom motion velocity gamma, and also the viewing angle theta. So we can describe the delta in this way, and the gamma and the theta are observable. It only can be determined from the other observations. Also, delta is also an unobservable parameter. So, Iulia and Padovani described this the property of Blazars, and they showed us that the violent active of Blazars can be explained if the radiation is beamed to us. So, we should use beaming effect to explain the observation properties. Also, the detection of strong and viral gamma rays, the very, very rapid variability in gamma ray band also suggests that there is a beam effect. We can also, for the one-sidedness of the jets, can be explained by Doppler also boosting effect, because if there are two jets, when this jet point to us, the other just in the other direction. So this one is very, very bright, but this one is faint. So it's like only one jet, one side of the jet. We also found that the high polarization is also associated with the beaming effect. From the observational property, from observational viewpoint, we found some sources have superluminal motion, just as Elena said a few days ago. So all of this suggest that the beam effect is in the Blazars. This is for the superluminal motion, Elena talked about this. I just skip this. But I want to say that even though the Doppler factor cannot be observed, but if we have some method, we can get the Doppler factor. If we get Doppler factor and we also have the superluminal motion velocity, then we can use these two relation to get the gamma, to get the knowledge factor and the viewing angle. We can get this from these two equation. We can get this. Also, in the case of delta equals to superluminal motion velocity, then the gamma can be estimated in this way, and the viewing angle can be estimated from the superluminal motion velocity. You can see this analysis work, and also this is from the Euler and Baikal and Padovani. For the superluminal motion, if we do observations, if we do many observations, we can find that the two parts, the core and the ejected part, we can do observations. We can find their distance bigger and bigger, longer and longer. Then we can put it in this diagram. This is the observation time, and this is the distance of the two components. Then we can say, then we can do the linear correlation. Then this loop will just show us how fast the small point, the point goes away from the core. And this we say it is as proper motion velocity. Then we use this and the distance. This distance we can notice the numerous distance, and this is the redshift of the source to us. Use this observation, we can get the superluminal motion velocity. It is expressed in this way. If you're interested in this, you can read this paper. So if we, from the observation, we get the proper motion velocity, we can get the superluminal motion velocity, or we can call it apparent velocity. So for example, for this source, the observations indicate that the proper motion velocity is 0.11. So we can, from this source, the redshift, we can get the luminous distance is so many MPC. From this one, we can get the apparent velocity. If somebody interested, I think we can ask the student to get the apparent velocity beta APP. And if we get the beta APP, we can estimate the viewing angle. Just use the method as another point on that. And I also want to ask, does this apparent superluminal motion violate the relativity theory? Because this velocity is much greater than the speed of light. Now I talk about the beam effect in the gamma ray emissions. We hope to know. I hope to say that the gamma ray emissions has a strong beam effect. First, we can get the available Doppler factor from the literature, from these references. Then we calculate the gamma ray luminosity, and if we put the gamma ray luminosity as the y-axis, and the Doppler factor to power 3, we can get the result. We say the luminosity is proportional to its increase with the increase of Doppler factor. It means that it perhaps tell us that the gamma ray luminosity is boosted. Also, we use the radio band values, radio observations, because in the radio band there is a compact core, and also there are some extended structure. We use the emission from the two parts, one from the core and the other from the extended part. We can get a parameter called the core dominance parameter. The core dominance parameter can be calculated in this way: the emission from the core to the emission from the extended part. This is the core dominance parameter. So we can get the core dominant parameter for Fermi Blazars. We get so many Fermi Blazars have core dominant parameter, and so many we also connect so many AGNs. They have no core dominant parameter, so we can compare that. So we get a sample of so many sources, and 630 have Fermi emission, and the rest have no Fermi emission. So we just compare these two subsamples. We can compare their core dominant parameter. We found that for Fermi Blazars, their core dominant parameter the distribution is in red, while the Blazar have no gamma ray emissions. We show it in this dashed line. So we can see Fermi Blazars have higher core dominant parameter than the non-Fermi Blazars. This result suggests that Fermi Blazars have strong beaming effect because this core emissions is boosted. In 2010, Howard observed that radio polarization in Fermi detected area is higher for the invested sources. It suggests that the source detected by Fermi, then there should be the polarization is higher. It perhaps suggests that the emission is boosted during the period. And also, Wears in 1992, Wears got a sample of AGN or Blazars, and they found that the polarization, the optical polarization against the core dominant parameter in this way. It means that the polarization increase with the core dominant parameter. So we yesterday we talked about that there is a difference between X-ray selected beam object and radio selected beam object. There are some difference. One of the differences is that XBL have low polarization, while RBL have higher optical polarization. So we hope to explain why the polarization in radio in RBL is higher than XBLs. So we consider this using the two component model. If the emission is from two parts, one from the beamed, another from the unbeamed, then use if we assume that in the source frame, the emission is also from two parts, and we assume that in the source frame, the intrinsic flux is F times of the unbeamed one. Then we think we also assume that for the emission, the intrinsic emission in the core is also composed of two parts. One part is polarized, another is unpolarized. Because the emission from the core is boosted, then we can use this concept. And from the observation point of polarization, in one direction there is a maximum, and in another direction is the minimum. So for the observations, you use the maximum flux minus the minimum flux, and divided by the sum. Then we get the polarization. Using this, we can get the polarization can be described in this way. Here. So we can get this final relation. This is the F means that in the comoving frame, the emission from the beamed is F times of the unbeamed, and the delta is a Doppler factor. And this is a power, and this PIN as we say it is the intrinsic polarization. So from the observation, we can get that the observed polarization should be associated with the Doppler factor. In this way, if RBL has a strong beaming factor, then they should have higher polarization than XBL. This is our final formula for the equation to describe the polarization is associated with Doppler factor. From this relation, we can get that the polarization is also associated with the core dominant parameter. This is if F delta P should be the core dominant parameter. So we can get that the polarization is associated with the core dominant parameter. This is our result, just like the observation result of VS. So I think this can be just like this one. We can from this formula we can also get that the polarization is correlated with the variability of for example in the optical band. This is our result. Okay. Now I go to the Hubble diagram of Blazar objects. Yesterday we talked about the beaming effect, some beaming factor, and we also remember that in the first day, Junhui Liu said about the Hubble relation it is in the 1929. The Hubble showed a result for 24 nebula. The distance is associated with, is correlated with the velocity. Afterwards, in 19 1931, the Hubble and his work also get more sources and get this very nice correlation. We call it the Hubble relation. If we take a sample that have the same absolute magnitude, we can get that their magnitude, absolute magnitude, and the visual of the magnitude is associated with the distance. If we use the distance, if we get the if we describe the data for the redshift is small, we can use this to use the redshift to approximately to describe the distance. In this way, if we have the same absolute magnitude, we can get the visual magnitude is correlated with redshift in this way. This is the Hubble diagram. In 1987, Babbage and Hewitt used a sample of Blazar objects to investigate the Hubble relationship, but they found that they have 28 Blazar objects. 20 Blazar objects has the redshift of a galactical redshift, and the rest 8 have emission redshift. They found that for the redshift for the galaxy, for the redshift for the Blazar objects has galaxy redshift. They occupy this region just around the line, but for Blazar objects has emission redshift. They deviate from this line, this region. They have also found that all of these sources are sometimes the OVV, and they will deviate from this lines. These sources are also very variable. So then perhaps perhaps this source is not the same group as this one, because they do not fit the same Hubble relation as this one, and all of these sources are X-ray selective Blazar objects, and these are radio selective Blazar objects. It is perhaps that for the RBL, they have emission redshift. They have boosted, so their magnitude their source is bright, and the magnitude will lower. So we just consider that because in Fabry and the Rios obtained the efficiency of conversion of accurate matter into energy for spherical and homogeneous non-relativity beam region can be described in this way. So this is the efficiency of conversion. This is the luminosity. This is the variation in luminosity, and this is the corresponding the time scales. So this efficiency can be described in this way: if this value is greater than 0.1, it means that beam effect is included. So we can use this to get the observed eta. Just if we have the numerosity variation and the corresponding time, we can get the observed eta. Also, if we use the intrinsic variation and the corresponding time, we can also get the intrinsic eta. But from the beaming effect, the observed numerosity can be described in this way. This is the Doppler factor, and the observation time also correlated with the intrinsic time scale in this way. So we can get the observed eta in this way, and the intrinsic in this way. So if we can see the Doppler factor, we can get that the Doppler factor can be calculated by observed eta and observed and intrinsic eta. But for the eta, if for pure acceleration the value of eta is smaller than 0.1, so this is the upper limit for the intrinsic one, for the pure and not the spherical acceleration. But for the nuclear actions, reactions, the eta is 0.007. So we can choose their middle value as the intrinsic eta. In this way, if we get the observed eta and we use the 0.5 as the intrinsic one, we can get the Doppler factor in this way. So we can do observations to get the time scale and get the corresponding numerosity variation. In this way, we can get the Doppler factor. This way, so when we can see the beaming effect, the observed flux density is correlated with the intrinsic velocity, flux density by Doppler factor. So Doppler factor, we can get Doppler factor, and the observed flux density we can change it to the magnitude. This is observed magnitude and this is intrinsic magnitude. So we can use this way. We can get the intrinsic magnitude equals the observed magnitude plus this value. So if we can get the Doppler factor and the spectral index in the optical band, we can get the intrinsic magnitude from the observed magnitude. We found that the intrinsic magnitude is much larger than the observed magnitude. This means that for this one example, if we know the Doppler factor, we found that the intrinsic will move to this place. So we calculate the Doppler factor, then these eight sources will move in this way. This is the result for the. So in this way, we get Doppler factor in the optical band for RBL, and finally the RBLs will move this way to this place. So this is the extra BL and this is the RBLs. So now for observations, RBL occupy this place, XBL is in this place, and after the correction, we found this the plus also moved to this region, and finally we get this result. So we can say that the RBL and XBL should be intrinsically they are the same class. When we put the corrected RBL and XBL in the observed OVV in the same plot, we found that XBL and the correct RBL, they occupy this place, and this the pluses are the other OVs we have not corrected them. In this, so this plus we don't have Doppler factor, so we cannot we didn't get the intrinsic magnitude. If we put radio galaxy and XBL and the corrected RBL, in this plot we found they follow the same relation. So we propose that BL-like objects and FR1 are the same class. I think they are unified. And we also put the FR2 with the galaxy morphology. Then they also follow the same Hubble diagram. So we propose that BL-like objects, FR1 and FR2 galaxy, they are the same class. And in this plot, we put the OVV and FR2 with the quasar morphology. They are the same class. So in this work, we propose that BL-like objects is unified with FR1 galaxy and FR2 with galaxy morphology. And when OVV is correlated, the unified with the FR2 galaxies. This is our result. So when we found that the XBL, therefore for the different wavebands have good correlations, we also hope the RBL have the same correlations if we have Doppler factor to get the intrinsic flux density. But if we use the Doppler factor we have had from the optical observations, but we failed if we use the same Doppler factor to get the intrinsic radio, optical, or X-ray flux density, we cannot get the good correlations. It perhaps that the Doppler factor in different band is not the same. It is not the same. Actually, in 1989, Giannini proposed that the Baikal velocity increase with distance. From distance, if the gamma is increased with distance. So that means the Doppler factor is also different. They also increase with this distance. Just as Alana also, Alana also showed that the gamma is also increased in this way. So if the gamma is changed from different wavebands, perhaps we can construct a relation for different bands. In this way, we think we just get this formula for different band with the Doppler factor, just because from the observation at the optical band we can get a Doppler factor, and we have the radio we have a Doppler factor at the radio band, so we just try to get the empirical relation. This relation we got. I think this relation, we use this relation, we can get, if we use the optical Doppler factor, we can get the expected value. And then when we compare this known values, they're almost the same. I think this consistent with each other. So we use this relation. If we have the optical Doppler factor, we can get the X-ray Doppler factor and the radio Doppler factor. Then we can get the intrinsic radio flux density and the X-ray flux density, then we can analyze the correlation between radio, optical, radio, X-ray for all of these sources. Then we found that for the observations, this is the radio selective BL object. For the observation data, there's almost no correlation. This is the X-ray and the radio band. This is the optical and the radio. The observed value is this way, and this is the X-ray and this is radio and X-ray. So the correlation is not so good. But if we consider this Doppler factor effection, and we can get the intrinsic flux density, we found this is the intrinsic value that show better correlations, also better. Okay. Makagani found that if we consider the spectral index in the plot, they found that the radio selective BL object occupies this region, and the X-ray selective occupies this region. So they occupy different regions. Makani said that if X-ray XBL boosted by about 200 in radio flux, and optical in 30 times, then the XBL will move to the radio band, RBL, the region. So we hope to do this if we use this relation. We have optical Doppler factor, we can get a radio and the X-ray Doppler factor. Then we can get the intrinsic flux density in this way, and this is for the frequency. We can calculate the intrinsic spectral index. Then we can do this for RBL. Then we found the intrinsic flux density and get the intrinsic spectral index. We found that this sources will move to this place. For the this is the XBL, this XBL, this RBL. If we correct their flux density and get the spectral index, they move to this place, this to this place, and this to this place. So we think when we use the Doppler factor, we can get the intrinsic values almost the same with the XBLs. So the Doppler factor is very important for very important for BLF objects, and it is hard to. We cannot observe the Doppler factor. We can only estimate the value of the Doppler factor. There are some methods. There's some method. First, we can see from the Gisellini's work, they assume that the standard synchrotron mechanism to predict they can predict the X-ray emission from the standard SSC, and they compare the observed X-ray value with the expected value. If there's a difference, the difference is explained by the beaming booster, then can estimate the Doppler factor. Also, Doppler factor can be estimated from the radio densities variation, and also relatively they use the equitation of energy between radiating particle and the magnetic field. They use so many methods. Now, first I show this the Doppler factor determined by SSC. This was proposed by Gisellini and his whole works. The Doppler factor, they just use the standard synchrotron self-component component model by comparing the predicted and the observed X-ray flux. Then they can get the Doppler factor in this way. This here, Fm and Fx are the flux density in the radio and X-ray band, and here are the mu m is the synchrotron frequency cutoff. They assume that this to be this value, and the delta theta is the core size in millisecond. And nu b is the synchrotron high frequency cutoff. They assume this one, and here f alpha is a function of spectral index in the radio band. So if we have the VLP observation to get the size and the flux density and the corresponding flux density, and we can use this X-ray observed X-ray flux density, we can get the Doppler factor. This is the Giannini's work, and for the Van Taucher and his co-works, they proposed a method to estimate the Doppler factor. Just decomponent the flare component used this way. Just they can get the variation magnitude and the corresponding time scale. They use the time scale and the variation amplitude, and to get the brightest temperature. And they assume that the intrinsic brightest temperature is this value. Then they can get the Doppler factor in this way. In 1993, Mattox proposed that they use the gamma ray and the X-ray to get the Doppler factor. They think that if we can get the gamma ray emissions, it means that the optical depth for gamma collision is not so high. And they assume that the X-ray, when he just consider that when the gamma ray and X-ray pass through the X-ray field, the collision optical depth is not so high, and they can get the optical depth in this way. This is the X-ray flux density. This is the energy of the gamma band to get the gamma emission. This is the spectral index. So they can use this to get the optical depth. If we assume the optical depth is less than 1, then we can get the Doppler factor in this way. We get the Doppler factor here. We describe this in this way. It's much, I think it's much convenient to get the Doppler factor. This is the Mattox's proposal. So it's if we have time scale and X-ray flux density and the gamma ray energy, If we have time scale, have X-ray flux density and gamma ray energy, we can get the Doppler factor. So we use this way to estimate the Doppler factor for example of Blazars, and we finally found that the Doppler factor for FSIQs is greater than that for XBLs. So it means that the FSIQs is much strongly beamed than XBLs. In 1995, Baikal and Karpatos consider another scenario. They just consider that the gamma rays passes through a X-ray, to temperature disk feed. Then the gamma ray can be observed. It means that also the condition of the optical depths, the condition and the pair production optical depth is not so high. Then we can use this consideration to get the Baikal and Karpatos proposed the optical depths, the formula, and we also based on the Baikal and Karpatos' formula, and we can see that the observations is not only from the axis, but from there is an angle between the jet and the net of sight. So we can describe the optical depth in this way, and this here the phi is we can say it's the emission is just from a cone, and this is and the phi is the cone, the semi-angle. So here the tau is the optical depth. It depends on the supermassive black hole, super black hole masses, and this viewing angle, this distance. This is also we can say it's the emission size. Here, k is a constant. It depends on the accretion disk. And for the emission size, we can constrain then use the observed time scale. We can describe this in this way. If we think that the gamma emission not isotropical, but only from a cone, then the gamma emission not from 4 pi, just from the solid angle in this described in this way. So we can express the luminosity in this way. Here this phi is this phi. So from this formula, we can get a Doppler factor. You can describe it this way. We also found that this from this formula, we found that the optical depth, if we choose phi and set the m is a constant, then it changed with the viewing angle in this way. We found there is a minimum for this one. So we assume that the minimum tau is 1, and then from this formula, we partial this tau and the partial phi, we can get the minimum place. This will be 0. So we can get another formula. This is now we can get the tau is described in this way, and this is the emission size this way, and this we assume the tau is then we assume tau is 1, and we also partial tau, partial phi, we can get the minimum. The minimum should be 0. So we can get 4 formula, and we have 4 factors. So we can use this to get the 4 parameter theta. We can get the theta, delta, m, and the phi. So we can calculate this. And we applied this to a sample for gamma ray sources, and we found that the mass for RBL and XBL, BL and FSIQ are almost the same. So we think there is no difference or in masses between BLAC and FSIQs. So in this part, we assume that the gamma ray is not isotropic just from a cone, and we can get the values for delta, emission size, and phi, and massive black hole masses. We use this formula to assemble for family Blazars. For Blazars, we found that if for the sources with emission lines, we found the gamma ray numerosity, and the disk numerosity in this way, and here the stars, the opposite stars are FSIQ, and the rest are BLAC objects. And we found that there are some sources. Sometimes they are FSIQ, other times they are RBL. We call this change-Luger Blazars. In these regions, some of these sources are change-Luger sources. So we propose that this region should be the aplanine zone. It means that the sources for these regions, sometimes they are RBL, sometimes they are BLAC objects, sometimes they are FSIQs. So this is the change-Luger region. So we have another method to calculate the estimated Doppler factor. This is based on the work by Junhui. But they obtained that the radiation of power is correlated with the disk luminosity. That it means the jet is correlated with aggregation. In this way, they obtained this result. But for the radiation power can be described in this way. This is from the jet. So we can use gamma ray luminosity to reply for to stand for the jet, the jet emission, and the disk as the aggregation luminosity. That means this relation just tells us that the aggregation and the jet are correlated. They get this result. But when we analyze their sample, we just separate BLAC object and FSIQ. We separate them, and we found the different correlations. This is if we put them together, it's the same. But if we separate them, we have different relations for these two parts. So if we use gamma ray luminosity to replace this one, and the emission and luminosity to replace this one, we can get the Doppler factor. So this is our consideration, and we can get two formula, one for FSIQ, another for BLAC objects. So we can use this to get the Doppler factor. And we to do so, we make a cross-checking between Fermi catalog and SDSS. We can get so many sources has emission lines, and we can use we use this value, this formula to get the Doppler factor values, and here is the result. The result. And we get the luminosity. Also, sorry. Yeah, this is the luminosity distance distributions for our cross-checking magnetic sources, and we get their luminosity of a gamma ray band, and we can estimate the Doppler factor, and also we show the luminosity of proton against the single John peak frequency. We found the RBL, FSIQs occupy this region, and BLAC occupy these regions. So it means we can use the SVM to separate this. So this region should be FSIQ, this region should be XBLs. This is the Doppler factor. Now we have the largest Doppler factor sample. It's about 1,000 sources have Doppler factor. So another method for Doppler factor estimation is use the unification model, because the BLAC object is correlated, is unified with FR1 and FR2 galaxy. Then we can use this to estimate the radial Doppler factor for BLAC objects. We consider a sample of so many BLAC and so many FR1 and FR2 galaxy. We compared the extended radial luminosity between BLAC objects and FR1 and FR2 galaxy. We found the extended luminosity are almost the same. So it suggests, it also supports that BLAC objects and FR1, FR2 galaxy, they are unified. But their core emission, the core luminosity is quite different. This is the FR1, FR2 galaxy, and this is for BLAC objects. And we think the difference is from the beaming effect, the beaming boosting. So we think if FR1, FR2 galaxy and the BLAC objects are unified, then the intrinsic should be the same. So we can use this. For FR galaxy, we can get the correlation between the external emission and the core emission. Then we can use this as the intrinsic relation for BLAC objects. So this is for FR galaxy. FR galaxy, their emission should be intrinsic. This is for FR galaxy, and this is and we think for BLAC objects, the intrinsic luminosity should be the same as this one, and the difference is from the beaming factor. So we can use this to get the beaming factor for BLAC objects. So we get this one. We get this value. I don't go. Yeah. This is our result, and we also compared our result with others. It almost there are some I think there are some similarity between ours and the others. So now I show you something about the two components of Blazars. We know, thanks to the radio technique, we found that the radio sources have a compact core and extended component. How about that for X-ray band? But X-ray band have no so high resolution, we cannot separate the core and the extended. But we can see this just as Brown and Murphy, they can see that we can use the radio band to estimate the compactor emission for X-ray and the extended part for X-ray. How to do that? We can consider the X-ray luminosity and the radio band, the core emission. We can do the correlation, and we think also for the X-ray band, we can assume that the X-ray band should be the same, and we can plus this one. This is from the extended part. This is the extended part. So we can think that if the X-ray also composed of two components, one from the beamed and the other unbeamed, you can write this in this way and get this way. Now, if we use this can also be rewrite in this way. This k is a constant. This constant is almost the same as this one. Okay. Then for X-ray band, the extended part luminosity should be written in this way. And if we have for the radio band, if we have the beamed part, we can get the X-ray X-ray value, and for the curved and extended one. So, if for the extended one, we can get this in this way, extended one. But here we have two parameters. One is this alpha tx and the gx. Alpha tx can be get from minimizing this value, and for the k also we can get. K also we can get from this value for this method, because for the X-rays the totally emission is also from the two component, and here the gx can be written this way. Gx is written this way. This gx it also depends on the theta and the beta and alpha x. But if we know beta cosine theta, we can get gx. How to get this one? We can get it from the radio band. So in radio band, this is just the core dominance parameter. We can get it, and here we have the value from this work. And if we have this one, we can get beta cosine theta. And if we insert this to this place, we can get gx beta theta. So we can in this way we can get the X-ray total. So the X-ray total we from the radio band value we can expect the X-ray the total value, and this can be in X-ray band we have the observed luminosity. We use the induced observed one minus this one, and to get this one to minimize this total sample, we can get the k at the RTX, and then afterwards we can get the X-ray extended luminosity for each source. This is. For this way, we tried to separate the X-ray band for so many sources, and finally we found also that for X-ray band the core dominance parameter is also associated with the X-ray flux density, the spectral index. And also we used this to as a big sample for so many sources. We separated the X-ray into two components and get this with a statistical result. And from the observations, we found that in the radio band the spectral index is correlated with the core dominance parameter. So this is the observation. We hope explain this relation. We used the component model to describe, to explain this because the observed flux density is from the jet part and the extended part. And this is the two-component model. And we use this to describe the flux density, and this is the observed one, and this for the core and for the extended, and the part this partial new, we can get this formula, and also the minus the same type of minus one, we will get this one, and finally we can get the alpha. This is the radial spectral index is correlated with R over 1 plus R. So alpha J means from the bind one, and plus 1 over 1 plus R alpha extended. So the total for the whole emissions, the alpha tau is correlated with R in this way. If we assume alpha J and alpha UMB, we can get the alpha total with the core dominance parameter. This is our result. So if we assume this one, we can get this different curves. This curves, we think this has explained the core observation result. So in this talk, we give some introduction for the beaming effect in Blazars, and we showed the Hubble diagram of radio selective Blazar object and X-ray selective Blazar object. But we know that for the observations, the RBL they do not operate to the Hubble diagram. But if we get the Doppler factor, we get the intrinsic magnitude. We found the RBL, intrinsic of RBL and XBL for the same Hubble relations. And we also proposed that the RBL and XBL, the others, are unified, and the Blazar objects with alpha 1 and alpha 2 galaxy, they are unified. And we propose that the OAV, or we can say FSIQ is unified with the FR2 quasar. And we showed the Doppler factor estimation method, and also we separate the X-ray emission into the core and the extended component. Also, we derived a relation between the spectral index and the core dominant parameter. So, if we, okay, I said a few things. I think it's interesting that to discuss the relation between the Blazar object and the FSIQs. You know, Blazar objects has no emission line, or emission is weak, but the FSIQ have very strong emission lines. But from the continuous emissions, they are almost the same. Then what is the difference? What is the difference between FSIQ and the Blazar objects? There are some argument for the difference between Blazar and FSIQs. Someone proposed that Blazar objects have smaller viewing angle, and this way, Blazar objects have strong beam effect than FSIQ do. But these statistic results don't favor this one, because from the sample estimated Doppler factor, we found that the FSIQ Doppler factor is larger than Blazar objects. So this argument is not correct. And also from the supernormal motion and the Data factor and the Doppler factor, we also found that the viewing angle of Blazar objects is larger than FSIQs. So this argument is not correct. Somebody think that we do not need to consider their relation, because FSIQ and the Blazar object different subclass. So this is no more discussion anymore. Some people think that peer-like objects and FSRQs, they are in different evolution stage. Perhaps the FSRQ having strong emission lines, they evolved to peer-like objects. If this consideration is right, then we can propose that the central black hole mass of peer-like objects should be larger than FSRQs. But from up to now, the statistically said that the masses of black holes for peer-like objects and FSRQs are almost the same. So we don't think there is an evolution process between peer-like objects and FSRQs. Then what is the difference? How to explain the difference in the luminosity, in the emission luminosity? When we explain the difference in the emission lines, we also should explain why they are almost the same continuum emissions. We propose that in the coherent frame, the emission from the core to the extended emissions, the ratio is different. If the ratio is different, we think the peer-like object, the ratio should be larger than the FSRQs. Should be larger. From the two-component model, the observed emission can be described this way. This F is a ratio between the intrinsic jet to the extended one. The F is unknown. This is Doppler factor, and this is the extended emission. Then if we can have some method to get the F, we can know whether there is any difference between them. Now, how to do that? Because the core dominant parameter can be written in this way. This is the beta theta, or just the distance to follow the two-component model. So if we want to get the F, we should get the RT and the gamma. We can get this one. How to get the gamma? We can consider a sample. They have Doppler factor and the superluminal motion velocity, and also the core dominant parameter. So we should get the samples with the three parameters. Now here, if we have Doppler factor and the superluminal motion velocity, we can get theta and the beta and the gamma, okay? Then we can calculate the F. So we consider two samples. The first sample is from the, we have the first sample. We got a 37 superluminal value sources. This is for the total sample. This is beta, and this is log R. We have log R, and we can get the Doppler factor from this work, and then we can calculate the gamma, theta, and then we can get the F. We get the F. So we have, for FSRQs, we get the median value for F is in this way, so minus 0.5, and for peer-like objects, the median value is 0.9. So FBL is about 20 times of FSRQ. This is from this sample. Another sample where we get the 41 superluminal sources, that's the beta in this region, and this log R, we have this one. And the Doppler factor is from the Van Taja's work. So we can also use this sample to get the F for BLAG objects and FSIQs. We also, for this sample, BLAG objects, they have also larger IF than FSIQs. So, so we think this difference can explain the difference in the emission length, because from the observations, we think the emission is from the extended one and the beamed one. And if for the beamed one is dominate the emission, then we cannot see the emission length, or the emission is weak. And if the if the emission from the core is very strong, the emission length will be very weak. If the F is small and the emission from the core is not so strong as the extended one, or almost the same, then we can see the two parts. So we can see the emission length and the continuum length. So I think this can explain the observations difference in the emission length. This is our distribution for the F. And also we can see that it's all, I think we can compare our result with other work. For F, Euler and Badawani, they think that from their work we can find that the F is in this region. And from this work, the F should be log F should be 2.3. So this value, all value for F is doesn't conflict with other result. So we can also get the F from the polarization and R relations in this way, because when we consider the optical polarization against Doppler factor, we can for FSIQs in this way, and for BL objects this way, we can also get the F for FBLs is larger than FSIQs. Also, I think we can use the F difference to explain the difference in emission length between BL object and FSIQs. And I think I finished my talk here. Thank you again.
So we have 2 minutes for questions.
Sorry, I got behind my.
I have not really hard question, but in the slide of 2-component emission, you use logarithm, but it doesn't have base in slide.
Okay, thank you. So yeah, I should show this. From the radio observations, we can find that for radio sources, for the Blazars, they have a compact core and some extended structure. So from the core, we take the emission from the core as the core emission, and the others for standard for the extended emission. Right?
I had more mathematical question.
Okay.
It was why we don't have base of logarithm,
like
exponent.
Log 10, log 2, what it was?
Log 10, log 2.
The base of the logarithm. She's asking about the base.
Was it natural or decimal logarithm?
Sorry. Let me go back to.
I think it's natural.
Huh?
I think it was natural.
The logarithm. The question is whether the logarithm is natural or decimal or something else.
It's natural. Yeah.
Logarithm of
Natural.
Yeah. Natural. Yes. Thank you. Okay. Thank you. Okay. Good. Yeah. I should write this clearly. Thank you very much. And the next time I show you this. Okay. Thanks.
Very short question.
Okay.
I would like to continue yesterday's question of Dmitry Vladimirovich, in which he asked why we try to make classification based on the cosmological redshift, but in the other way. So I suppose the farther we see in the universe, the younger it is, and the mechanism may be different, which is going to be discriminating this data. So can you please, I'm sorry if I missed this, but can you maybe repeat what are the difference between the blazars which we see in the near universe and in the distant universe?
Very good question. Very good. Very nice. Very question. Yeah. I think so. We think now perhaps it's time for us to discuss this problems, because we have the WST. I think we can GWT. I think we can now get the very early sources, and now we can discuss this the difference from the ancient early times and the very from, I think, from the higher redshift to the near redshift, we can get the differences. So I think now is the time for us to discuss. Okay.
So let's end lecture 8.
Thank you so much. Thank you. Okay. Thank you.